So we've finished the trigonometry. Okay. The next couple of units, we're going to go back to certain types of functions. Like remember in Unit 2, we graphed radical functions, specifically square root functions. Unit 3, we graphed polynomial functions. Okay, the ones that look like this, lots of turning points. This unit, we're going to look at exponential functions. And then the unit after that, we're going to look at its inverse, which are called logarithmic functions. Some of you, I believe, are familiar with logarithms from chemistry. Okay? But we're going to start with an exponential function. How do you tell whether a function is exponential? Well, it's got an exponent, or sorry, it's got a variable in the exponent. Okay? We haven't dealt with ones like this before, where the unknown, the variable, is an actual exponent. And it takes this form. Remember, f of x, we could also replace with y if we wanted to. And an exponential function will have a base c, which could be a number anywhere from 0 up to infinity. And then the variable is the exponent. So when we first started these functions, like other ones that we did this year, we wanted to see what the most basic ones look like. Like when we started with radical functions, we started with the very basic one, y equals square root x. You know, what does that one look like? And then we went from there. We did transformations. We're going to do the same thing with this. Okay? So we're going to look at a couple of exponential functions, one where the base is 2 and the other where the base is 3. And the best way to start these things is with the table of values to see what shape it takes. So for y equals 2 to the x, I'm not going to use all of these. I'm just going to use negative, 1, 0, and 1. We could use more, okay, to get us a better idea, but this should give us a good enough idea of what the shape's going to look like. So if x is negative 1, remember what 2 to the negative 1 is? 1 over 2, right? Because remember, 2 to the negative 1 is the same, 2 to the negative 1 is the same as 1 over 2 to the positive 1, which is 1/2. So negative 1 is 1/2. How about that? What's 2 to the 0?
1.
1. Anything to the 0 is always 1. And what's 2 to the 1? 2. Well, that gives us an idea that it's going to be a curve. Okay? And you can see it's going to take off like that, because if you think about 2 to the second, it's 4. 2 to the third, it's 8. It keeps getting higher and higher and higher every time I add an x. Now, what about behaving the other way? Okay? Like, does it go below the x-axis? Does it go along the x-axis? Think about it. Like, what's 2 to the negative 2? 1 over 2 to the 2, which is 1/4, right? What's 2 to the negative 3? 1 over 2 to the 3, which is? So it keeps getting smaller and smaller and smaller, right? So like what's, if x is negative 1,000,000, it's 1 over 2 to the millionth, which is a really small number, but does it ever hit 0? No. So x will never, or sorry, y will never become 0. Like this will get smaller, 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 but it will never touch the x-axis, because y will never equal 0. So that's the shape an exponential function takes. If we did 3 to the x, and if I did -1, 0, and 1, well, 3 to the -1 is 1/3, 3 to the 0 is still 1, and 3 to the first is 3. So it's going to be a little bit smaller here. It's going to be the same value here, but it's going to be here. So it's going to climb faster on the right. But it's going to do the same thing on the left. It's going to go to 0, but never touch it. Okay? So you can see that's the shape an exponential function takes. If I did 2 to the 4th, it would climb even faster. It would look like this, but then it would go up like this. And as this number gets bigger, it climbs faster and faster and faster, almost to the point that it's climbing vertically. Okay? No matter what number I put in for the base, 2, 3, 4, 5, 6, there'll always be the same point on all of them. What will that point be? 0, 1, right? Because it doesn't matter what the base is, as soon as you raise it to the 0, it's 1. So each graph, no matter what C is, as long as it's bigger than 0, will contain 0, 1. All of them won't have an x-intercept, because we just showed that as it moves to the left, it approaches 0 but never touches. And remember, y equals 0 is the x-axis. What's the domain? Should be able to get that from the graph. Negative infinity to positive. Or if you want to write using the other notation, either one is acceptable. What's the range?
Not including 0 to 100.
Right, so what do I put around the 0?
Bracket.
Bracket?
Right.
Parenthesis. Remember, parenthesis means don't include, bracket means include. Remember, we said it will never touch the x-axis. So we need to add to each graph a dashed line showing where a curve approaches but will never cross. What do we call that kind of line? Asymptote.
Can't try to be less than 1.
No, unless you flip it.
But if I have y.
Oh, sorry, y greater than 0. My mistake. Sorry,
Can you do y to not 0? Or no,
no, it has to be y is greater than 0. So in this one, there exists a horizontal asymptote. At the x-axis, which we also call y equals 0. Finally, what's the behavior of the graph? If the base is bigger than 1, the graph increases left to right. So as I go from the left to the right, it's going up, it's increasing. If C is a fraction between 0 and 1, it actually decreases left to right. And we'll see an example on the next page. Okay. Here we have another couple of ones. 40 to the x should be pretty easy. Let's do -1, 0, and 1 again. 4 to the -1 is 1/4. 4 to the 0 is 1, 4 to the 1 is 4. So that's, it looks like the same shape as the previous ones we did, but it climbs faster. So notice it increases as we go from left to right. Okay? But what if this is a fraction between 0 and 1? What is 1/4 to the -1? Flip and make this positive. So it's 4 to the +1, which is 4. So it's there. 1/4 to the 0 is still 1. And 1/4 to the 1 is 1/4. So notice what's the relationship between, they are horizontal flip or reflection, right? One is a horizontal reflection of the other. No, that's more polynomial. What? Yes, but you can't. You always have to move. You're always moving. And if you don't want me to notice, you can't do things like this. Because that's not, like, all I see are heads and then this. What do you think I'm going to notice? It's heads sitting still, sitting on necks, and then arms going like this. Which one am I going to notice? Oh, yes, thank you. Thank you for getting me back on track. Yes, you do have to draw that as part of your graph. Okay. So you can see what the shape of these exponential graphs is going to look like. We can also go in the reverse order, where you're given the graph and you're asked to write the equation. Guess what I noticed now? I noticed Rena's head almost separating from her neck because she was like this. You okay? All right. All I saw was a neck and the blackboard. Her head completely disappeared. What do you think this one would be? Well, first of all, it's increasing to the right, so it's going to be bigger than 1.
Right,
Yeah, it's a little hard to see, but you've got 0, 1, you've got 1, 5, and then if you went 2, you'd get up to 25. So it is 5 to the x. Okay. So notice, like I said, the bigger this number gets, the base, it's almost going vertical. Okay. Last thing I want to talk about, and a couple of you will know this from essential math, but here's a really good application of exponential functions. Okay? Like, imagine for a graduation gift, you got $1,000 from a family. Okay? And you wanted to put it away. You wanted to just say, listen, I'm going to invest it. And I'm just going to pretend like I never had it. And I'm not going to look at it until I'm 40. Okay? How much would that be worth in 40 years? Could you get a pleasant surprise? Okay? Well, let's find out. But let's do this. Let's say you had let's say you got a $4,000 gift. Okay? And the instruction from your family member was, you have to promise me, you have to put it in an investment and you can't touch it until you're 40. Okay? And the way interest rates are going, you get 4% a year. Compounded annually. What that means when interest is, like, first of all, 4% interest rate, how much would you earn after 1 year? $4,000, 4%. $4,000, 4%. How much would you earn? $40?
Oh, 10. Oh, wait, $10.
All right. Yeah, more calculator. What? 40 times 4?
40 times 0.0.
Why 40? It's 4,000. 4,000 times 0.04. You get $160 after 1 year. Okay? Remember, you've got to keep that money in there. So that $160 does not come to you, it goes back into the investment. So at the end of the second year, we're not taking 4% on 4,000 again. We're taking 4% on your new amount, 4,160. That's called interest on interest or compounded interest. Again, how can I not notice you? Okay. So all we see is this. So it is actually exponential because you take 4% of 4,000, get your new amount, take 4% of that the next year, get your new amount, take 4% of that. So it keeps, you keep multiplying it actually by 1.04. That's exponential growth. Okay? So it is exponential. Because you're making interest on the interest and what we call principal from previous years. If it was something called simple interest, that means you get $160 a year. Okay, it would just calculate 4% of 4,000 every year. So you get $160 every year, 20 years, you'd get 3,200. Okay, but this is that's not exponential growth, this is, because you're calculating the percent on top of percents. Okay, So let's see what this looks like. And then we're going to develop a formula. So make sure I have this right. End of year. Okay, so we'll just start for a couple of years, and then we'll see a pattern develop, and we can make a formula out of it. So at the end of year one, remember, our principal, the amount we originally invested, is $4,000. We're about to calculate the interest. What's an easy way to calculate interest? Don't just do 4% of 4,000 and then add it. There's a quicker way. 4,000 times 1.04. Because what you are doing is you are taking your principal and multiplying it by a whole amount of principal and 4%. So if you do 4,000 times 1.04, you're going to get 4,160. At the end of year two, you had this. Okay. Actually, no, I'm going to change that. Sorry, I'm just changing it to 4,000. Let's call it the original principal. So what happens at the end of year two? Well, you take your original, times it by 1.04 to figure out how much it's worth after year one, times it by 1.04 again to find out how much it's worth after year two. So remember, this is year one, and then this is year two. And when you do that, you get $4,326.40. $326.40. At the end of year three, take your original and times it by what? 1.04 times 1.04 times 1.04, or 1.04 to the third. Save yourself some time. Oh my God.
Oh my God.
Catch us up on Canada 3G.
It's deep fake.
What does this work out to? $4,499 and 46 cents. Okay, how many years have passed since you turned 40? 23? Let's assume we're all 17 right now. Or do we want to assume we're all 18?
18.
Let's assume we're all 18. So that means at the end of year 22. Remember, you've forgotten about this money. How do we find it? Take your original times by 1.04 times itself 22 times. Because notice If it's 3 years, the exponent's 3. It's 22 years, the exponent's 22. So do 1.04 to the 22nd, and then multiply that amount by 4,000.
This is supposed to be easier calculator with the glasses.
Yes, it is.
Yeah, they should.
9,000.
That's what I'm like.
$479.68. You've more than doubled your money. Okay? So think about that. Focus. Think about that when you invest. Think about that if you need to borrow money, because banks will do the same thing to you. They will charge you interest on the interest. Okay? That's why when you borrow money for a few years, you actually have to pay back more than you borrow. And that's called the interest. That's the charge. That's what the bank charges you to borrow money. Okay? And how can we get a formula out of this? Well, think about it. To find the amount of an investment or the amount of a loan, what were we doing here? We were doing the principal times 1 plus the interest rate raised to the number of years we invested for. Or it would look like that if we used variables. Principal, we would use capital P. Interest rate, we would use a little r. Okay. Number of years, we would use n, or we might use t. Okay. Useful formula to remember, though, if you're borrowing money or if you're thinking about investing.